Now let's talk about the generation of exponential generating function for this sequence. Yes, this can be transformed into a specific sequence, but first let's try to identify what does this notation mean. Take note that this notation is actually for the notation of permutation. Hence, this is actually equal to n factorial over n minus r factorial. And take note that we are going to have a sequence first for the function following the pattern where r starts from 0 to infinity. Okay, so how do we show it in a specific form? Take note that if we have this notation, you can have here, say for example, for your first, your 0, so you have actually n factorial over, you have n minus 0 factorial. Then the next term, n factorial over n minus 1 factorial. Plus, then the next term of the sequence is n factorial over n minus 2 factorial, right? And so on and so forth until again you will reach here n factorial over n minus r factorial. If we are asked about the exponential generating function of the sequence, we'll be using the idea of this. If these are your terms until you have a sub r and so on and so forth, this is actually equal to a sub 0 plus a sub 1 x over 1 factorial plus a sub 2 and then times x squared over 2 factorial plus so on and so forth until you will reach a sub r x to the power of r over r factorial. Okay, so with that, let's try to illustrate this one here. You will get actually here n factorial over n minus 0 factorial for a sub 0. Now then, plus your a sub 1 is this n factorial over n minus 1 factorial over, sorry for that, this is still over, or times, or rather, times x over 1 factorial, right? Plus, let's have here the next term at the bottom. You have here plus n factorial over n minus 2 factorial x squared over 2 factorial, and so on and so forth until you will reach here the term n factorial over n minus r factorial times x to the power of r over r factorial. Okay, so this is the form of its exponential generative function, but this can still be simplified. I would like you to proceed here. This rth term. For our rth term, we can actually have here n factorial over n minus r factorial times x to the power of r over r factorial, right? Okay. However, if you're going to multiply that, you will have here n factorial times x to the power of r over n minus r factorial r factorial. What is this form? Okay, I'm talking about this form here. This is actually a combination n combination r. Okay? That would mean for our rth term, we can create a certain combinatorial notation for x to the power of r alone. This should be true for all the terms inside, such as this, because if you have this first term, a second term rather, you'll have here n factorial over n minus 1 factorial, 1 factorial, where your 1 is actually your r times x. So basically, all of these are in this form here, this form, which can be translated. So I'm going to translate now this notation at the bottom, this actual form here. So pardon with me. I'm going to translate all of this here. So your first term is still this, okay? So you will have actually n factorial over n minus 0 factorial, right? Okay? Or just simply equal to, can we remove that now? N factorial. That's our first term, okay? Or just equal to 1. Then, let me move this down. Sorry. For our second term, as mentioned, we can actually group this. Okay? So you will have plus n factorial over n minus 1 factorial 1 factorial. Without simplifying 1 factorial, you have your x. Plus this next one here, I'm talking about this. So you will have n factorial over n minus 2 factorial 2 factorial x squared until you reach again this term. You will have plus n factorial over n minus r factorial, x to the power of r, and so on and so forth. Why do we do this? Again, because this form can be written as n taken r, x to the power of r. In short, this is where r is equal to 2. You have n taken 2, x to the x squared. This item here is actually n taken 1, x, and this is actually equal to just 1, or you can have here n combination 0 to look at a specific pattern here. Why are we doing this? Even if we're already done with the expansion or the generated function, because we would like to find out if we can represent this in terms of a power series. In that case, we will have here the power series summation of this term, okay, n combination r, x to the power of r, as n is as r equal to 0 to positive infinity. This is actually the power series that can define our specific given sequence here of permutations from 0, where r starts from 0 to infinity. So we started with permutations. We're able to come up with the relationship using combinations, and then we're able to simplify it in this power series, which are actually in turn equivalent to a form before using binomial expression, or binomial theorem, which follows this specific form: a to the power of n minus r, b to the power of r starts from 0 to positive infinity. So b stands for x. So our a is actually just equal to 1, because if this is 1, regardless of what is the exponent, it's still as it is. So this is actually the entire function here, generated, the exponential generated function from this given sequence of permutations where r starts from 0 to infinity is just equal to this form 1 plus x, a binomial expression raised to the power of n. This is according to the binomial theorem previously discussed in the previous chapter. Nevertheless, this is an indication that even if we have permutation numbers, or our sequence has permutations, so we were able to come up with a combination for this perspective and brought us with the binomial theorem. Okay? Thank you very much for watching.